Okay, hi. We're gonna do buoyancy problem now. Let's read through it and then we'll examine how to approach it and we'll start solving it. It says a helium balloon of some volume is released from the ground and starts to rise. Okay, so we have a helium balloon. The volume is not given and it's gonna be found that the volume doesn't matter. What is its velocity when it reaches a height of 2,000 meters? So as it's going up, it's gonna gain velocity. What is its velocity when it reaches 2,000 meters? What is the maximum velocity that it reaches? So assume that the density of helium is 0.179 kilogram per cubic meter. So that's the density of helium. Density of air is 1.29 e to the minus h over 8,000. So that means at the ground level, the density of air starts 1.29, but it starts thinning out as you go up. So it's a non-uniform density. We've actually done a problem previously, so you could look at that video if you want, where I have examined this density function and I've done some questions based on that. So I'm using the same density function, okay, that I've used before. So how do we approach a problem like this? This problem is a good illustration of Archimedes' principle for an object that is sinking or rising. So basically this is the opposite of the sinking case. If you put a material that is more dense than a fluid, if you put that material in the fluid, it will sink and it will accelerate down. If you put a material in a fluid and the material is less dense than the fluid, it will start rising. So this is a case where the object will rise, right? So you have, imagine here's the fluid. In this case, the fluid is air, okay? So this is the fluid here, air. Then you have the balloon. You release the balloon and air buoys it up, right? You have the buoyant force and then you have the weight of the object. I'm going to assume in this case that the weight of the actual balloon material itself is negligible, but if we wanted to include that, it wouldn't make the problem that much harder. We could just add the weight of the balloon and we could analyze that. But let's assume that the balloon is large enough to where most of the weight of the balloon is in the form of the actual helium gas itself, okay? So now we have here the buoyant force is mg. So since the material itself, the helium, is less dense, the buoyant force is going to be larger, right? So we can write this vector a little smaller. So it starts to accelerate upward, right? Okay, so what is the buoyant force? The buoyant force on the balloon is equal to the density of air times the volume of the balloon, right? Times gravity. The balloon itself, since it's fully immersed in the fluid is air, okay? It displaces a volume of air equal to its own volume, right? And so this is the volume of the balloon. And then the density of air is this. So remember, according to Archimedes' principle, the buoyant force on an object is the weight of the fluid that it displaces. Well, the weight of the fluid is the density of air. And since it displaces the same volume as its own self, then we multiply by V, then we multiply that by gravity, right? Now, mg, that's the weight of the helium balloon. That's equal to the density of helium times volume times g, right? So now we're going to say Fp minus mg is equal to ma. So apply Newton's law and Fp is going to be winning and then we're going to calculate the acceleration that way, okay? So let's erase some of this. And you have here minus mg, density of helium Vg, and that's equal to Ma. What's the mass of the helium? The mass of the helium is density of helium times volume. Density of helium times volume times A. Notice the volume cancels out. So the volume of the helium balloon doesn't matter. And then the density of air, this is where we put the non-uniform density, right? Density of air is equal to 1.29 e to the minus h over 8,000. We have our 9.8 minus density of helium, which is 0.179 times 9.8, and then that's equal to 0.179 A. Well, we could divide this by 0.179 0.179, 0.179, and then we're going to get, this one is going to cancel, and then we get what? We have here 70.6257 e to the minus h over 8,000 minus 9.8. So this is the acceleration. We have some number, which is this times this over this, times e to the minus h over 8,000 minus 9.8, okay? So now how do we calculate this? Remember, acceleration is the rate of change of the velocity versus time, right? So we have here dv dt, okay? But it is a non-uniform rate of change of velocity. In other words, the rate of change of the velocity versus time actually depends on the height of the object. So how do we approach that? Well, we could do it this way. We could say dv dt is equal to dv dy, dy being the height, right? So I'm measuring here this way. I'm putting the x and y axis on the ground, and I'm measuring the height, and the height is equal to the y, the rate of change of how fast the vertical component of the distance is increasing, right? So I'm going to say dv dt, dv dy times dy dt, right? dv dy is the rate of change of the velocity with respect to the height, times the rate of change of the height with respect to the time. Now dy dt is actually the velocity itself. So we have here v, this is v, times dv over dy. Okay, now this is in the form where I can integrate it, right? dy goes over there and goes over there, so we have here 70.6257 e to the minus h over 8,000. H I'm going to just replace by y, e to the minus y over 8,000, and then I'm going to take the dy and put it here, minus 9.8 dy, and that's equal to v dv. Now I can integrate this from v initial to v final, and I can integrate this from 0, since the 0 is the initial height, and we wanted to know what's the velocity at 2,000, right? So we put here 2,000. Okay, so now we integrate this. So how do we integrate? Well, this is an integral that is pretty easily doable. It's not too hard. We can just say 70.6257. The integral of e to the minus y over 8,000 is negative e to the y over 8,000. And then the reciprocal of the 1 over 8,000 comes out, so it becomes 8,000. Okay? And then the integral of 9.8 dy is just 9.8y. Okay? Okay? So now this is very important. After you integrate it, you're integrating from 0 to 2,000. Don't just assume that when the 0 is going to yield 0 for the lower limit. So we have to say here 0 to 2,000. You see? We have to actually put that in, and you will see that it doesn't give you necessarily 0 when you use the lower limit. What happens to this one? V squared over 2, V initial to V final. Okay? So let's put that all in. So what happens here? When you put 2,000 into here, you're going to get, so this negative is going to come out like that. 6,505.5866. Okay, so this is this negative. Then you have e to the, oh, I do need a negative here, right? So when I integrate it, I can't get rid of this negative. So you have to remember, e to the negative x dx, the integral is what? Negative e to the negative x. If I have e to the negative ax dx, it's negative 1 over a e to the negative ax, right? So that's what I was using. So I can't change this negative to a positive here. I have to have that negative, and then I have to bring the negative out, and then the 8,000 has to come out as a 8,000 in the numerator, right? Because I have to reciprocate it. So now we're going to do e to the negative 2,000 goes here, 2,000 over 8,000. Okay? And then you're going to have minus 2000 times 9.8. Okay, then you're going to subtract, minus 0 goes into here. So when you subtract that, this one gives you a positive, right? Because it's already a negative. So you're going to have positive. And then when you put 0 here, either the 0 is just 1. So notice it's not 0. And then when you put 0 in here, that actually does give you 0. And then you have here what? V final squared over 2. We're assuming the balloon starts out at rest, so the initial velocity is actually 0. So that's all you have. Then whatever number we get there, I got 105378.79. I can double that and then square root it. Okay, so I got V final is equal to 459.08 meters per second. So after 2,000 meters, which is 2 kilometers, okay, so you're going to get, the velocity is going to be going pretty fast. What would have been the answer if the density of the air was constant? Okay, let's just quickly calculate that and see if our answer makes sense. V would have canceled. If this was constant, it would have been 1.29, 9.8 minus 0.179, 9.8 equals 0.179a. And then you divide by 0.179. Cancels, 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 cancels. And then that would have given us what? Right? And now that acceleration would be constant. So what would the final velocity be after it has ascended 2,000 meters? V final squared is equal to V initial squared plus 2AD. Since the initial velocity is 0, you get 60.8257 times 2,000. So it's a much quicker process if it's a uniform acceleration, right? So we have here 7 meters per second. So that actually makes sense. If the density of the air had been uniformly the same thickness, the same density, it would have reached a velocity of 493 meters per second, going much faster. But because the density is getting thinner and it's getting lower, the velocity is actually less than it would have had if the density had been uniform. Okay, so our answer makes sense. It's about 40 meters per second lower. Okay, now let's answer the second part of the question, which is what's the maximum velocity that the balloon will reach?